started. So you're being recorded from now on, please be aware. I will turn our video off because I recognize that the connection is very unstable. Okay, please forgive me. Okay. So, welcome back. We are today continuing with sampling variability in the central limit theorem. I hope you can see my screen well and hear me as well.
Yes, it's visible.
Okay, good. Okay, I go in full screen mode. So we are now working on sampling variability in the central limit theorem. So today we will be talking about population versus sample. Hi, Rishab. So we will be discussing.
Hello, Professor.
Population versus sample. We will be talking about sampling distribution at the central limit. Hi. Which is very central to essentially build the bridge between a sample and the population. As you can imagine, this is quite important, particularly for hypothesis testing, where essentially you need this general concept to essentially understand what hypothesis testing essentially entails. So, but more about this in the next lectures when we actually talk about hypothesis testing. Today, we will just discuss the central limit theorem. Then we will be talking about experimental versus observational studies. And lastly, we will be discussing prospective fundamental differences between the study designs, and you will understand the subtle differences and why these are important and why both design. Yes.
Your voice is breaking a lot.
I was afraid this would happen. Yeah.
It's breaking a lot.
Okay, can you please all turn the videos off? You too, Rishab. Maybe this improves it a little bit. I hope it's going to be better now. Otherwise, I need to record it. Okay, so both of these designs are basically important. So experimental versus observational studies do and places within hypothesis testing and research design and study design. Equally, prospective versus retrospective studies. In the realm of epidemiology, in which I'm basically working, we do a lot of retrospective studies. Prospective studies are essentially usually studies that are being prospectively conducted based on insights that have been gained from retrospective studies. But more about that once we get there. Open Intro 4.1 and 4.4 are the essential chapters in Open Intro that will be basically allow you to get the theorem. And Open Intro 1.3 to 1.5 gives you an overview of the study types for you to read up. Yes.
So, Professor, it's breaking a lot. Like there are total gaps of 5-6 seconds in between.
Okay, let me switch on the phone.
Okay.
I hope it's better now. Can I?
What, Professor?
Can you hear me now?
Yes, Professor. We can hear you.
Is it now somewhat better? I hope it is. I logged back out and back in. Sorry for this hiccup. This is rather inconvenient. Is it okay now? Let's continue for now. If it doesn't work out, then we need to do this in a different way.
Okay. Yeah, it's better now.
Okay, good. Okay, then let's go back. Let's not go full screen. I try to keep everything on the low burner. Okay, so we will be talking about experimental and observational studies, prospective and retrospective studies today. So let's carry on. Okay, so we have talked about population versus sample. So a population essentially can be defined on any population of interest that you may have, that you may be interested in. And the sample is meant to represent your population to preserve something that is called external validity or generalizability. So now, as you can imagine, if you draw a sample from a population, not all samples will be the same, right? They will not 100% represent the overall population. They will be different in terms of these overall statistics, in overall central tendency parameters, as well as the variability statistics. So you see this represented here, basically. So we have here population with a mean of 78 millimeter Hg of diastolic blood pressure, whereas the sample means are here at 75, 67, and 71.3. So all of this essentially serves to basically quantify statistics, changes, dynamics within the samples, and use these to essentially draw inferences of the overall population. So this is called what is statistical inference. So you see this also kind of reflected here. So whenever there's a talk about the population mean, you will see this reflected as the so-called mu, the Greek parameter, or the Greek letter mu. Whenever we're talking about the sample mean, we look here at X bar, which is characteristic for sample mean. So there's some vocabulary that needs to be paid attention to. So we essentially, we're looking at study units or sampling units, which are individual elements of interest. We have a target population that essentially we would like to describe, which essentially the sampling is a part of. The study population is the population from which the actual sample came. Systematic differences between the sample and the target population would be referred to as the selection bias. So this is a very often quoted term, and you hear this quite often, particularly in the context of randomized controlled trials and studies that were conducted. Because as you can imagine, you're drawing samples from a population, and this population essentially does not always reflect the overall population. So this sample population may and sometimes be substantially different actually from the overall population. So selection bias is definitely something that we will quite frequently find in the context of conducted trials. We also have now the sampling frame, which is a list of all units in the study population that is being used for sampling. Again, here the notation, whenever talking about population parameters, you will be talking about population mean or population standard deviation. This is referred to as either mu or the Greek letter sigma. If you use sample statistic, you will refer to it as English alphabet, sample means and standard deviations is X bar and S for standard deviation. So whenever it comes to sampling, there's different sampling strategies that are basically being used to draw samples. So when you think about it, so the simplest way of sampling would be to really draw a random individual from a population, right? So this would be absolutely random. And in a perfect world, this would actually be the most favorable approach, where you have absolute randomness in your sample and where the mean in your sample actually really represents the mean of the population. Other ways that are being done, and the decision between the sampling is mostly done between all these sampling strategies is mainly done for logistic and organizational reasons, because as you can imagine, it's quite difficult to actually sample from a population. So this being said, it's really an organizational problem how you actually will be able to sample from your population. So another way to essentially do that is to employ systematic sampling. One form of systematic sampling would be, for example, to select single numbers randomly between 1 and 30. And you basically would then select individuals from these numbers. Another way would be stratified sampling, where you have, and this is often done with comorbidities and with gender, where you essentially use simple random sampling within the strata that you have chosen. And with a predefined n in each stratum, you can to some extent make sure that there's an equal distribution amongst these strata characteristics. So if you have here, for example, you have diabetics, and here you have patients with congestive heart failure, and here you have normal individuals, or you have here males and females. Within the strata, you essentially are able to select equally distributed between both groups. So this is stratified sampling. Cluster sampling would be something different, where you essentially would be stratifying as per clusters, clustering of individual of potential recruitees that are to be approached for your study. So one possible approach would be clustering as per county. In my world, it's, for example, it's a dialysis clinic, or it could also be as per hospital or emergency rooms, or whatever cluster you could think of. You can actually do cluster sampling. One of the problems with cluster sampling is that you will have systematic differences between the clusters and from the clusters to the overall population. This is something that you will need to deal with to some extent, either with the sampling per se, or you will have to deal with this programmatically and analytically. So essentially you do sample random sampling within each cluster. And one of the downsides is that the sample variance will be larger than the sample random sampling, where you pick from the overall population, because the number of clusters essentially will contribute to the occurrence of variance in your sample population. Excuse me just a second. Sorry for that. Just caught a little bit of a cold on the flight. Okay, so we have sampling strategies. And this strategy will not only affect the way you will be dealing with your data, it will affect generalizability. And one of the biggest problems with that is that you will get so-called non-probability samples. These non-probability samples are essentially because you will be recruiting volunteers that are willing to participate in a study. And that's actually one research topic on its own right, to what extent this actually preserves generalizability, because some opinion papers and some analyses that have been done in terms of generalizability of randomized controlled trial was showing essentially that most studies that have been conducted measuring whatever you could think of, antihypertensive medication, any other medication, are essentially not representative of the overall population to which you essentially will use this medication on. And this is true for many interventions that you will be finding in the medical literature. So that's actually a huge issue, and to some extent also concerning, because that medication that was effective in your population, your sample population, your study population, may not be as effective or equally effective or not causing as many side effects as it did in your study population, but in the overall population, it may be entirely different in terms of the dynamics. So this is obviously a problem. And so here are some examples for non-probability samples, and this could be A, volunteers, B, patients at a cancer clinic, or patients in a dialysis clinic, as in our case, in my real life job. And particularly with dialysis, you have a kind of a non-probability sample, which is particularly pronounced because patients come to dialysis and they're at the machine for 4 hours. So for this very reason, it's like they are much more inclined to participate in studies because they're there anyways, and they're 4 hours there. And some are really just very interested in our research, and they participate because they're learning something about our research, they learn something, they get to exchange with our research coordinators or with our fellows that are MDs from all over the world. So there are many factors that essentially render study populations potentially non-probability samples. Another factor is here the so-called and often quoted convenient sample, and this is something that you will find in many contexts. So particularly psychological studies, for example, we conduct surveys. So many surveys are, for example, conducted at places of gathering, where you have a lot of people coming together, and they basically they gather, and they're very easily approachable by research coordinators to basically be recruited. Can you see my screen now?
Yeah, yes, Professor. Yeah, we all were trying to say, like, we are not able to see the screen, so it was difficult for us to understand.
Sorry for that. This was because I logged out. So I am now on slide 10. So when I talked about sampling strategies, this was 6, 7, 8, and 9. So there are because of the breakup, we were a little disconnected. So I hope you can hear me now well, and you can essentially see these slides.
Yes, we can see now.
Okay, great. So these are the sampling strategies, and I'm now on slide 10, talking about the non-probability samples. So the problem with these non-probability samples are that you do not know the probability of selection. So you cannot really quantify, you cannot really adjust for it. So this selection bias is sometimes not avoidable, and it's really necessary that you accept it. And for this very reason, you can't really get out of it. But yeah, it's because you don't know the probability of the selection, you can't really account for it, you can't really rectify it in a way. So this being said, the perfect way to essentially randomize and random sample would be what you see here. So these are GIS plots of a geographic area. So you have here, and I'm zooming in here a bit. So you have here essentially some certain areas which you essentially see places of gathering and places where more people live. So with random sampling, you would basically pick absolutely independent, randomly conducted or randomly assigned spots on this map. Whereas when you do a systematic sample, you actually get a system in there that potentially could introduce selection bias. If you have stratified random samples, you essentially see here the different colors that essentially will also introduce some potential selection bias. And as you can see, it also changes the variance amongst both strata, because here you have a greater area and you have more points. So obviously the variance is going to be smaller because you have a higher number of participants. Whereas here you essentially will have relatively smaller sample and you will relatively have more variability. If you do non-probability sampling, like here on the very right, you see clearly that there is a selection bias present, and you likely will have differences to the overall population that would be represented by something like this on the very left. So these are the factors you need to pay attention to whenever thinking about sampling. Okay, any questions on sampling? If not, then we can carry on, and we will continue to talk about experimental and observational studies. So as the name implies, with experimental studies, you do have an experiment that is basically subject of investigation. So you do have an experiment, an intervention that is currently being used. The most important study design in this context is really the randomized controlled trial. And the randomized controlled trial is essentially the highest level of evidence that you will find in study design and in research. So because of this randomization between treatment and control groups, you would consider all distinguishing factors between the groups to be balanced. So let's say, for example, you study something that is most effective in diabetics, and you create a treatment group which contains a higher proportion of diabetics. So you will automatically see a stronger effect in your treatment group because you have more diabetics and your drug is more effective in diabetics. So if the opposite is true and you have more diabetics where the drug is more effective in the control group, you will have the opposite effect. So that means that actually the effect that you see in the treatment group will essentially disappear because in your control group, the drug was now more effective actually because of the higher proportion of diabetics. So this is called a so-called confounder. And these confounders are meant to be randomized away by the randomized assignment to treatment and control groups. Of note, and this is something that we will discuss in later lectures in a little bit more detail, experimental studies are essentially the only way how you can prove causality. And this is one of the major limitations of observational studies, that you cannot prove causality, because everything that is retrospective, you do not have the luxury of randomization. So you do not randomize to treatment or control group. You do not have this balance of confounders. And because of the potential presence of confounders, you have a really hard time to prove causality. As a comparable kind of distinction, you have now observational studies. Observational studies are essentially something that is usually done preceding experimental studies. As you can imagine, if you do a real intervention on ethical grounds, this requires much more knowledge about the effectiveness and efficacy of your intervention. So you cannot just study a blood pressure medication just because you think it was effective. You need to first understand, how did other blood pressure medication work? How much can you administer to your population and to your study population to essentially be not harmful? So you will have insights from previously conducted studies, and based on these previously conducted studies, you essentially will be designing your experimental studies. So for these observational studies, you essentially have no observation, no intervention, and by that you only observe dynamics and you build your insights, your research insights, based on these observations. So you're looking at here three major study designs in terms of the observational studies, which are basically here cross-sectional. So cross-section is really a study that is conducted at one point in time. And in this one point of time, you draw a considerably randomized or random sample from the population at this particular time. So the enhanced data that essentially we have for the final project available is one very famous example of such a cross-sectional observational study. The New York City HANES, which is basically an NHANES conducted on New York City inhabitants, New York City on New Yorkers, is a New York specific local example. And then we also have, and we have looked at some data of the BRFSS, this behavioral risk study that also was conducted by the CDC and also created a lot of insight into the dynamics of the US population. Secondly, we have then retrospective observational studies, which are essentially studies where you recruit your subjects that you run your analysis on based on the health status. So you either create it on the health status or on an exposure status. So health status would be, for example, a study design that is called a case control study, where you basically you pick easily described, you essentially pick subjects that have a certain disease, and you are quantifying within that population that has a certain disease the exposure of a certain characteristic. So let's say we have cases of lung cancer, because this is what we will be discussing later on. You have cases of lung cancer, and you basically quantify how many of your lung cancer patients have essentially been smokers. And then you compare it to a control group that did not have lung cancer, and you basically quantify how many smokers do we have in that population. So that's one way how to approach it. Another way to approach it is, for example, that you follow smokers over a period of time, over a prolonged period of time, and you basically quantify the incidence rate and the occurrence of lung cancer within smokers and those that are not smokers. In that very same way, you can also collect data in a prospective fashion, where you basically follow so-called cohorts over a period of time, where you essentially create a prospective cohort study, like the Nurses' Health Study is one example of that. So this would be where you say, okay, so you're a smoker now. I want to follow you over the next 3 years, and I want to see whether you die of lung cancer or not. And then you approach a non-smoker, and you tell a non-smoker, okay, so I want to follow you over the next 3 years, and I want to see whether you develop lung cancer. So this is prospectively conducted cohort studies. The problem with observational studies is, as per design, you cannot prove causality, as opposed to experimental studies, where you can prove causality because of the randomization and because of you being able to randomize away the confounders. Any questions on study designs? So this is now one of these examples that I have mentioned earlier. Okay, so we have experimental approaches. Experimental approaches are randomized studies. So one way how you can approach, for example, to find out whether smoking associates with lung cancer is to assign never smokers to smokers as smoking and non-smoking groups. You follow them for a couple of years, and then you see if the smokers develop more lung cancer as compared to the non-smokers. Another way would be randomly assign smokers to a no intervention or a cessation program, follow them for years and see who develops more lung cancer. Those smokers that you did not impose an intervention on, or those where you essentially have initiated a cessation program. So obviously both studies are a little bit hard to get through an institutional review board and kind of get approved by an ethical commission. So as a consequence of that, this will be fairly hard to study, not just hard, basically impossible. So as a consequence of that, and this is why this smoking is essentially a really good example, because only with such an example, you can basically emphasize the importance that observational research and epidemiological research actually has. So for example, you have here the three examples that we the 3D study designs for observational studies we discussed before listed with the very same example. So if you do a cross-sectional study, you essentially survey a sample of the population, and you find out whether they have ever been diagnosed with lung cancer, and then you essentially quantify how long they have smoked. Problem with that is that you will need an extremely high sample size, and you will need to study a lot of participants, because otherwise you will not gain much insights, which is one of the downsides, and this will cost a lot of money. Then you have retrospective research. So you recruit 50 cases with lung cancer. This is the example that I mentioned before. 50 cases with lung cancer and 50 controls who do not have lung cancer. And then you basically compare which group smokes more. What's the problem with that? The problem with that is that you essentially, and this is one of the downsides of a case control study, you need to very carefully select your controls. It's very, very hard to find good control groups that essentially will allow you to conduct case control studies. This is always, when you read case control studies, this is always the weakest part, and this is what you would need to draw most attention to, because this is usually where a lot of thought had to go into. And this is usually also the target of criticism whenever it comes to case control studies. Prospectively would, for example, did you observe groups of smokers or non-smokers for several years, and then you basically compare the incidence rates or the occurrence or incidence of lung cancer within both groups. So that's one way how to look at this. These are the observational studies. Any question on that? It's quite logical, right? It's just, I think it's nice to see it broken down that way, and to kind of have an opportunity to look at this data in that way, because it really allows for an understanding of how important the various designs are and what the weak points of the various designs are. So then let's move to the next topic. So we will be also talking about population versus sample. And this is super important because this essentially will be the basis for hypothesis testing, which we will do quite excessively for the second half of the semester. And population versus sample essentially is here depicted with participants in the cherry blossom run from 2009. And you essentially have 16,924 runners that competed in this race. So now these 16,924 runners, is this considered a sample or a population? So do we employ a population mean or a sample mean X bar? So given that these are all the runners, obviously this is considered to be the population of interest for our study. So now if we are drawing a sample now from our population, we essentially get obviously smaller sample sizes because we're only drawing 100 runners, but we get a distribution that does to some extent represent the distribution of the overall sample, of the overall population. So now essentially we are already one step closer to defining a so-called sampling distribution. So the sampling distribution is a distribution of a statistic for many samples taken from one population. What does that mean? You create here from the overall population one sample. This sample of 100 runners has a mean that will to some extent represent the mean that we have found here in this population. This mean is considered to be identical to that of the population. Is it really? Not necessarily. And this is why it's very important, because this sample population is essentially what is built of the sample statistics that had been calculated from repeated samples that you have drawn. So whenever we speak about the sampling distribution, we assume that we have drawn repeated samples from a population, and we have calculated sample statistics And we have essentially determined the mean for all of our samples. And this is important as a concept because if we are comparing a population distribution to a sampling distribution, these are substantially different, and the sampling distribution will be much more narrow. It will be more likely to follow a normal distribution, the shape of a normal distribution, and the mean of the sampling distribution is, because the mean of the means of all these means that you have collected to build your sampling distribution will be identical to the mean of your population distribution. And this is important as a concept because we will use these insights to essentially do hypothesis testing based on samples that were drawn from the population. So if we are looking at histograms and we're comparing histograms of the population versus histograms of the sample, the question here is the histogram of a sample an approximation of the population distribution or the sampling distribution? So the histogram here depicts something that shall resemble the population distribution. So it's an approximation of the population distribution. And the mean 35 of this sample is just one example of this sampling distribution. So basically the sampling distribution is built out of mainly means. So you can also use different statistics, obviously, but most commonly it's the mean. And this is also the one that is of interest here for our parametric tests. So we essentially quantify the mean of the sample. This means to represent the mean of the population, but only if you have repeated means, you get a sampling distribution, which mean will reflect the population mean. And this relationship between the sampling distribution and the population distribution is related to by the so-called central limit theorem. The central limit theorem dictates that the mean of the population and the mean of the sampling distribution is identical. And this is very important as a central concept, and it's one of the most important concepts in these basic hypothesis testing statistics. So the central limit theorem also says that the standard deviation of the population has a relationship to the standard deviation of the distribution of the sample means, which means that the standard error of the mean, so the standard error of this population sampling distribution spread, is the standard error. So this is the variability of the means of all the samples that were drawn. The relationship between the standard error of the mean and the standard deviation of the population is built by the square root of the sample size. So the relationship here is shown as the standard error equals the sigma, the population variability parameter, divided by the square root of the n. So this is a relationship that essentially is very important for hypothesis testing down the road. Thirdly, and this is another mainstay of the central limit theorem, is that for a large n, the shape of the sampling distribution of means becomes normal. This means that the more sample size your sample will have and the more samples you have drawn, the more likely the distribution of all your means takes the shape of a normal distribution, as you can see here. So I'm zooming in a bit. So you see here, sample means equals n equals 1. This is sample means n equals 10. So it becomes more and more normal the more you essentially get to higher numbers. So the sampling distribution of the sample mean of size n from a population having a mean mu and the standard deviation sigma the sampling distribution of the sampling mean is the following distribution. For a standard error of the mean equals sigma divided by square root of the n. So the center here is again the population mean, whereas the standard error around this population mean is sigma divided by square root of the n. So the standard error is essentially nothing else but a standard deviation, but it is basically kind of accounting for the sample size, and by that relating it to the sampling distribution. So it's not clearly an ordinary distribution, but it is the sampling distribution of your sample means. Does that all make sense so far? Are there any questions? If not, then let's carry on. So the standard error essentially tells us how much variability to expected sample statistics just by chance. So the sampling variability will decrease when the sample size increases. So that means that the sample mean will be very close to the population mean, and this variability will also decrease if the sample size increases. So the larger the sampling sizes, the less this variability. That's also very important to keep in mind for hypothesis testing. So the question here is asked, so how large is essentially a sample that is needed? So essentially, the sampling distribution of the sample mean takes more of a bell shape as the random sample size of n increases. So if the population distribution is skewed, then a larger n is needed because the shape will be closer to normal when the sample size is larger. You remember we saw that 2 slides ago, where basically it's shaped more in a normal shape, the larger the number was. So in practice, sampling distributions are supposed to be at around 30. So this is like this magic number of statisticians that basically say up until 30, you're basically supposed to think of it as potentially non-normally distributed, that you need to yeah, we talk about this another time. We talk about this with the t-distribution, but basically 30 is kind of a magic number which your samples should have at the very least for you to draw very solid inferences. It's easier if essentially the population distribution is approximately normal than sampling distribution that have been randomly sampled are considerably safe to also be considered to be normally distributed. So this is irrespective of the sample size, just requires really random sampling, which we have seen before is kind of hard to accomplish. But essentially 30 is definitely a sample size I would keep in mind, and this is basically the sample size that will often be quoted. So whenever you ask a statistician about how large should my sample be, you will always get the answer, it should be at least 30. So this is actually a common thread of conversation. So sampling distribution of a proportion, and this is where it's getting interesting. So essentially what you have, if you remember, we have the normal approximation. If you remember for the frequency distribution, with the normal approximation. So for a random sample of the size n from a population with a proportion p, you continuously draw various samples. You will get a proportion value in your samples that will essentially be, depending on the sample size, be fairly close to the proportion that you found for a certain characteristic in your population. So now the size of the sample will determine how close that actually is and how much variability, again, this sampling distribution forms around the actual real proportion in the population. So generally, it can be said that if you have a sampling distribution of a proportion, this will be normally distributed. It will be centered at the actual population proportion P, and it again represents with a standard error of this proportion estimates, which essentially is here standard error of the proportions, is given as square root of proportion multiplied by 1 minus proportion divided by the n. And this allows for us to do hypothesis testing on proportion. And this is something which we will likely do at one point. Yes, I think we do it with the chi-square test, yes. Any questions to proportions? If not, then we can move on to the applications of the central limit theorem. So the C-scores, which we discussed the last time. So for a sufficiently large n, the set calculated as x bar minus mu divided by sigma divided by a square root of the n. And this is now where we essentially dividing, this time not the sigma only, because we are not really on a population level anymore. At this point, we're coming already on a sample level, because now we are quantifying the set, not of an actual population, as we did last time with the frequency distribution. This time, we characterize our sampling distribution in terms of set scores. And this time, we're not characterizing it based on standard deviations like we did with populations. This time, we're doing it with standard errors. And this standard error is basically, as we know, the sigma, the standard deviation of the population, divided by the square root of the n. So it's again normally distributed with mean of 0 and the standard deviation that goes in increments of 1. With sigma known or estimated, you can calculate set relative to the sampling distribution and infer whether a sample came from a theoretical population of mean mu. So now let's think about that for a second. So you have, let's say you have a population mean of blood pressure, and that population mean of blood pressure, and this is the example that we will be doing at one point. You have a population mean of 120 blood pressure, millimeter Hg. So you essentially will now get samples that present with a certain distribution. And this sampling distribution will essentially be tested where you take the mean of the means of all your samples and you relate it in terms of your set score to the population mean. So you will want to know whether the samples that you have drawn are significantly different from your population mean. And there are ways how to do that. And this is what hypothesis testing will entail later on, once we get to hypothesis testing. But essentially what we're doing is we are calculating the set score based on our sample variability, quantified as the sample standard error of the mean, where we use the population standard deviation divided by the square root of the n. And by that, we characterize the distribution of the sample means, that we relate this mean of means and the distribution of the sampling distribution to the actual population mean. And we test whether this is significantly different. So you can do the same approach if you build a sampling distribution. So you get a sample and you assume that you do repeated sampling and you want to compare it to another value. You want to compare it to a blood pressure of 100. You can do it in the same fashion, because that set score will also allow you to characterize the difference, which becomes then the x bar from the mu. So if you replace the x bar with any value of interest, you can actually do hypothesis testing in reference to that value rather than the population mean. You don't replace the x bar, so you replace the mu. So if you want any other value, you want to calculate your sampling distribution to 140 or 160, you can replace the population mean and you can do hypothesis testing to any random number rather than population mean. So this, when it becomes a very powerful tool and basically can allow you to gain a lot of insight into the differences of your sampling distribution to your any value or to your population mean. Another application of the central limit theorem is the so-called 95% confidence interval. So the 95% confidence interval is essentially an estimate of an interval within which you're 95% confident that you will find your population mean. So this means that you basically you are quantifying your sampling distribution, and you mean to characterize your sampling distribution using this interval, this confidence interval. And based on that confidence interval and the wide this confidence interval is, so here we have from minus 1.96, you remember that Z scores can also be minus. So you have minus 1.96 and you have plus 1.96. And if that set is in between, you can essentially be you can be 95% confident and confident in both directions within that interval, your population mean will be located. So this becomes very important later on because you can use the 95% confidence interval for hypothesis testing without having to do the whole sample statistic. So, and why is this all important? Because all of this is the basis for t-tests, hypothesis testing using analysis of variance, the quantification of confidence intervals, which is going to be super interesting and super important for you to know, not only for the final project, but also for any scientific paper you may be writing down the road. So if we have a sampling distribution of a large enough n, even if we don't know the population distribution, the limitation will be that if it's not large enough, it's tricky because your population distribution may not be quote unquote normal enough, and your sample may not be large enough to essentially assume a normal distribution, which would be this magical sample size of 30. And the size of the sample does definitely matter, because the size of the population does not matter if you have only not matter if you have a fully representative sample following the normal distribution of a population. So these are kind of the limitations, but essentially 30 is a sample size you will be comfortable with moving forward. And the more normal the distribution of the population is, the safer you can act and conduct your analysis. So these are the summaries from what we have discussed. So important is really that the sampling distribution of the mean is related to the population distribution by the central limit theorem, which is essentially that the means of the population and the mean of the sample and the mean of all the samples of the sampling distribution will be identical. The standard error of the mean, the variability of these means relates to the population variability sigma by the square root of the n. And thirdly, that the larger the n of your sample is, your distribution will become more normal. And these are the important three mainstays and bullet points of the central limit theorem. And then we have some general classification of studies. We have experimental studies. This distinction between experimental and observational, please really keep in mind, because this is very central. And we have, of observational studies, we have a distinction between retrospective and prospective studies. Okay, so this is essentially all that I had for lecture today. Are there any questions? Or was all clear?
I was able to understand few of the topics here.
Okay, I'm happy to hear that. It's really very central. Just as a sorry, I'm so sniffling. The dry air is really killing me. Okay, so so I think this is, as a concept, it's considerably easy to grasp, but it's so super important, and this is why I made it a point to really have this lecture also to be part of this class, because these concepts are not always fully understood, and it's really, really important. So please keep in mind this relationship. The mean of the population and the mean of the sampling distribution are identical. The relationship between the standard error of the mean and the sigma of the population is given by the square root of the n, and the larger the n, the shape of the sampling distribution becomes normal. So this is really, these are really the most important take-home points of today's lecture. So if this was all understood, I'm very happy to hear that, and then we can essentially move towards our lab. And I'm a little behind today because of the technical issues in the beginning. So sorry again for that. This is very embarrassing. This was not meant to be. It's just always tricky when you don't know the strengths of the internet connection. Okay, so let's again open an R script. We have now a couple of things to do. All right. So we are now looking at data from Ames, Iowa. So for this purpose, we need to run line 3 and line 4. And these lines will essentially for us to load a data frame that is called Ames. So this data frame essentially is, so this is practice lab module, practice lab module 6, friend. So this data frame basically gives you all 2,930 houses in Ames, Iowa. And whenever we load data, what is the first thing we essentially do? The first thing is we have a look at what the data contains. So if we are looking at all these parameters here, we're seeing already, okay, so this is nicely characterized. So we have, of all these houses in Ames, we have a lot of data. And there's really all kinds of data. That's basement condition, fireplaces, fireplace Q, I'm not even sure what that means, garage, what year the garage was built. So they have really done a great job on characterizing Ames in Iowa. So what we want to use now, essentially an approach to build a sample that essentially contains, so create a sample of 60 houses. Oops. Okay, create a sample of 60 houses, describe the distribution of your sample and compare it to the overall population. What would you say? What would you say is the typical size within your sample, the overall population? Or is a state present what you interpret it typically to mean? So when I say size here, I mean this parameter. I want to understand the size of the greater living area. So this is how the size of the greater living area distributes. So given that this is square feet, it kind of humbles me as a New York resident because this is a lot of footage. Okay, this is a lot of footprint. Okay, so now we want to change a little bit, and we want to make this a little bit more resembling normal distribution. We do more breaks. Breaks equals 20. So now we get a little bit more of a normal distribution. Let's say it's a somewhat normally distributed, right-skewed data frame. And for now, let's treat it as normally distributed. Normally, you will always have to look in summary great living area, because by that you get an idea how much mean and median differs from each other, which is one of the characteristics of Normal distribution is that mean and median is equal, identically. So there's some difference. So it's definitely that the mean was, as we know, it's affected, right? So this is always how you will test data. So you basically compare the mean to the median.
Professor,
Yes.
I'm actually not able to get the data on my screen. I don't know why. The file's not working or something. In my case.
Okay. Can you use this code that I just dropped in the chat?
I copied this and pasted it, and it says environment is empty on the right-hand screen. I don't know why it's not running.
So what does it say?
It just says the error is in read character. Cannot open the connection in addition to warning images. Something like an error is coming up. It cannot load it up.
Okay.
Try to just like copy the entire thing, download file and load, and press Control Enter.
It's not working. I tried that.
Did you copy it from the chat?
Yes, Professor.
Well, I do not have it anywhere. Let me. Let me save it somewhere that you can that I can send it to you.
Bullo.
Oh. Okay, I'm dropping this in the chat now. If it lets me. Yeah. Okay, just input this data set. Try to input this data set. Load it somewhere where you have it quickly accessible, and that should allow you to do this analysis.
Professor, your
Quickly
voice just
accessible,
broke.
and that should allow you to do this analysis. I muted myself, sorry. Did you receive in the chat the file?
No, Professor. There's just the link. The old one.
In the chat?
Yeah, in the chat.
You did not
There is a document as well.
It's not showing on my screen.
So then let me put it as I sent it as an announcement. Can you go on Canvas?
Sure, Professor, I'm on Canvas.
Okay. Are you using a Zoom version? Do you have Zoom installed?
Yes, Professor, I have Zoom installed.
I'm not really sure why you can't see a chat message. Just refresh your browser and you get.
It worked. It worked. I got it. Thank you.
Okay.
Separate. Sorry.
Okay. No, that's okay. No. As long as you have to file. All right. So with summary, you will test whether the mean and the median are somewhat comparable to each other, and they fulfill the promise of a normal distribution. So just for you to know, and I would also want you to review that for the quiz next week, to make sure that we have, yeah, by the way, we have a quiz next week, right? You have that in mind. So that will be, it will be a considerably easy quiz, just with some of the basics that we have discussed. And so it basically will not be too hard. Just please make sure that you review the basic concepts that we have discussed. Okay, no, but keep in mind that when you have outliers, because of arithmetic dependency, the mean will be very sensitive to these outliers and will be pulled by the outliers in their direction, which means in our case here, with the outliers here on the right, we have basically our means pulled to the right, which we see here because the mean is substantially larger. It's not substantial, but it's a little larger than the median. So whereas the mode, which is the definition of the highest, of the most frequently occurring number or value, will not change at all because of the outliers, because there's no arithmetic dependency. Please make sure that you understand this concept fully. Okay, so now we are drawing a sample, and this sample is drawn with an easy code that is here. Okay, let's call it SAMP1. We use a function called sample. And sample essentially allows you to pull data from Ames, greater living area. And we want 60 of those. So sample 1 has now a certain shape and form, which we're going to look at now. And this is sample 1. So now we're describing sample 1. We're describing it again with the summary, sample 1. And we see, what do we note? Mean and median is actually, ooh, that was not good. That was not good. Okay. What we see now is that the outliers were removed because it was random sampling. So one of the beauty of samples is that we essentially see outliers more likely in the population. And samples tend to have less likely outliers. We clearly see that. And therefore, we also see here that the median and the mean are actually closer to each other. This is important to keep in mind because essentially this is where the standard error of the mean essentially is narrower with a higher sample size, but essentially it's also narrowing down the standard deviation because the standard deviation of the population is very wide, whereas the standard error of the mean is very narrow. So now we are creating a second sample, SAMP2, which is now sample Ames greater living area, which is again 60. So how does this one compare? So we just compare, we just take the same functions we used before, we're just renaming SAMP1 to SAMP2. So we have 1,556 and 1,514. So it's entirely different. It's a little bit more skewed essentially. So there's more skewed. So you cannot relate on it. This is why you need repeated samples, right? And these repeated samples essentially will then allow you to build something which is which is essentially a distribution of the sample means. So if we are taking more samples, we are actually not looking at the mean of a sample anymore, but we're looking at the distribution of the sample mean. So please answer these questions accordingly. And then also create a data set with 500 independent samples. And how do we do that? We do this again with our for loop. So we're creating now a data frame that essentially contains, so this is how you create a data frame. So you write df equals data frame, and then you create the first variable. The first variable is sample ID. And I'm just labeling this because this will basically give us a lead from 1 to 500. Then we create a second parameter, a second variable, which we label sample mean, and we're setting this NA. So what does this create? So when we look now at head and head df, we're getting now a data frame that contains a sample ID, and this continues 500 times. So head just shows you the first 6 entries. So we have 500 observation, and we have sample means set to NA. Because now we need these spaces. So we do now for I in 1 to 500 do curly bracket df I, which is the row, 2, which is the sample mean, equals mean sample of we do df, we do aims, create a living area with our 60 guys, with our 60 houses. So if we are saying now I equals 1, we're getting the first entry at df. Is it clear what I did here? So we have basically df. It goes in the first row, goes in the second column. It creates a mean of whatever comes after that. And this is consistent with that same formula that we did here. So this will create now a data frame concerning 500 sample means. And when you look at this, these are our 500 sample means. So now if you do summary of df sample mean, you see how narrow this is, right? This is a minuscule kind of df sample mean. And we do mean df aims, create a living area, 1,499 versus 1,497. So this how close you get with your mean from the samples to the actual mean of the population. And when you look at the ST, the standard deviation of aims, create a living area, you have 505. You do standard deviation of df sample mean, you see how small this sample mean is, right? And this is clearly because you are only looking at the distribution of the sample means. And this is how this looks like. This is a very small variability. And this was basically the distribution of the sample mean that we have just created for the aims data. So now we can do the random sample of 50 from price. So if we do sample Ames price, sale price. This was all 50. So now we have 50. We do a mean of that. We get 177,523. What's the mean of Ames sales price? 180. So you see that the differences are definitely this. Now let's see whether we're gonna get closer if we're doing our approximation of the sample mean. So now we do mean, now we do mean DF sample mean. You see the difference, right? You're approximating your population mean much closer by creating an iteratively calculated and computed sample mean for 500 times. And this is the idea that we're pursuing with hypothesis testing. So we're trying to create the golden point estimate for the mean, and we're trying to understand the variability of the population. And with the variability of the population, we're trying to characterize the variability of the sampling distribution. And we're using this for significance and hypothesis testing. 5,000 something. Okay. Okay, was meant to be 5,000. Sorry. But you get the picture, right? And this is just very important to keep in mind. So this is almost identical to the price, like $400 off. And these are independent samples drawn from a place of 2,930. So, are there any questions on that? I think we're a little early today. Was everybody able to follow? I hope that's a yes.
Yeah, Professor. Yeah, we were able to follow.
Okay, great. So, but this is a fun exercise, right? It very much it shows what the sampling distribution of the means actually is, and to what extent this is really helpful for hypothesis testing. Yeah, if no further questions, are there any questions? Anything like the quiz, for example? So the quiz essentially is just what we did so far. It's basically gonna test your understanding. It's open book, so don't sweat too much about it. You're gonna be fine. Just make sure in the slides you know where you find stuff, and you know where to look it up. And we're gonna do design of experiments, descriptive statistics, what we did lab day, probability distribution. And
Professor, when would this quiz open?
yeah, what?
Professor,
Yes.
when will the quiz open?
The quiz is open. I'm not sure I understand.
When will it open? Because according to it says that quiz will open at October 14th, 8 p.m.
That means on Wednesday.
Yes.
Professor, we
Yes,
have a
but
class
we're writing it in.
We have a
Okay.
class during that time.
Yeah, this is our class next week, right?
No. The timing that you have said that October 14th, the quiz would be open from the timings. We'll have a class in between of that. But we have another class.
Yes. But you don't have the access code, so you couldn't access it. No, we're gonna do it in this class.
Okay, we'll do the quiz in this class.
Yes.
Okay, so it means the quiz is not according to the time that has been given, but it will be according to it will be in the class only, right?
Yes, we're doing it in the class. Yes.
Sure.
Yeah,
Professor.
but don't pay attention to those times. It's
No
like I
problem.
opened it earlier. It's like so sometimes there are students that are joining from abroad. That's why the times are always different.
No problem.
But I will I will adjust those. Don't worry. No. But it's meant to be an in-class quiz, so I want to be there because in case you have questions, it's always of advantage that I'm right there. I think that makes a lot of sense. And next week we have a super interesting topic, and I hope you're going to like this one. So this is diagnostic tests. This is very relevant, particularly now in our days where everything was about testing, and testing was this huge conversation of 2020. I think it's super important to understand the basics of diagnostic testing. And so this is going to be a very exciting class. And then we continue with the estimation of confidence interval on 1021 in person again. Then I'm back in New York. All right. Any further questions? Any concerns? Please share questions and concerns on the discussion board. Happy to have a conversation also there. And if not, then have a nice evening, and we'll see you next week.
Sure. Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you. Have a good night now.